Welcome back to the deep dive. Our mission today, well, it's laser focused and honestly deceptively complicated. We are tackling the NFPA 13 standards, specifically diving into the 2019 edition. Now, this huge document isn't just some fire safety guideline. It's really the absolute global benchmark for designing and installing fire sprinkler systems. If you're in design, engineering, construction, risk management, this standard isn't just recommended reading. It's basically the rule book that keeps people safe and property protected.
Exactly. NFPA 13 is the undisputed foundation for fire safety in pretty much any built environment. But wow, it demands an almost impossible level of precision. We are talking about thousands of prescriptive rules. Rules where the difference between a compliant system and one that might just catastrophically fail, well, it often comes down to inches, or maybe specific PSI readings, or even the exact chemical makeup of whatever goods are being stored. So this deep dive is really about cutting through that complexity, helping you understand not just what the rules are, but crucially, why they exist. And we'll be paying close attention to some of the really tricky topics like seismic resilience and specialized hazards.
Okay, so we have an ambitious roadmap ahead. We're going to pull apart the structure of the document itself. We'll highlight the most significant changes introduced in that 2019 edition, the updates you really need to know about. Then we'll analyze the absolute non-negotiables, like water supply and testing. And then we'll dive deep into the specific rules governing those complex scenarios. Think massive storage facilities, specialized occupancies, and even how these systems need to perform when the actual ground beneath them is shaking. So consider this your shortcut to being deeply informed about the document that protects your assets. Let's unpack this.
Right. First thing we absolutely have to start with is the fact that NFPA standards, well, unlike foundational laws, they're never truly static. They're really living, breathing documents. They're constantly evolving based on new research, new technologies, and frankly, sometimes based on fire failures. So just knowing that current edition, the 2019 edition in this case, that's really only part of the story for compliance.
That's absolutely right. The official current standard at any given moment includes the base edition plus any subsequent official binding updates. And these updates, they come in two main forms that anyone dealing with enforcement needs to monitor constantly: tentative interim amendments, or TIAs, and errata.
And TIAs are probably the most critical ones to track. They represent urgent changes or maybe clarifications that are made between the official revision cycles. So if the NFPA finds a major flaw or maybe an ambiguity that could lead to, widespread system failure, they'll issue a TIA to fix it immediately. It basically bypasses the long consensus process. Errata, on the other hand, they're simpler. They just correct editorial or maybe graphical errors in the original text.
And the burden of staying current. That falls entirely on the designer and the installer. To help with that, though, the NFPA does maintain a dedicated resource site, which is helpful to note. It's www.nfpa.org/zotinfo. That page not only lists the existing TIAs and errata for NFPA 13, but it also offers an alert email notification feature. Honestly, if you are responsible for compliance, signing up for those alerts is pretty much non-negotiable.
Okay, so moving from how dynamic the document is to its actual authority. We need to talk about its legal standing. NFPA 13 is a private consensus-based standard, right? But it very often gets adopted into federal, state, or local law. And when that happens, it gains the force of law.
Right. And the distinction here is really key. NFPA explicitly states their publication isn't intended to urge actions that are non-compliant with existing local laws. You always have to consult the applicable local, state, and federal codes first. Ultimately, it's the local authority, having jurisdiction the AHJ, who has the final word. If the local law says something different from NFPA 13, you follow the law, period.
And this is kind of fascinating from a legal angle. Even when these documents get adopted and referenced wholesale in public laws, NFPA still maintains its copyrights. They make these standards available for public use and, private self-regulation, but they never waive their intellectual property rights. It stays a proprietary, expert-driven consensus document even when the state adopts it.
Okay, so now that we understand the legal framework NFPA 13 operates within, we need to address the actual language of the units, because this is where international confusion can often start.
Oh, indeed. The standard uses the International System of Units, or SI, as its primary measurement system. That's meters, kilograms, seconds. However, specifically within the international fire protection community, there are two non-SI units that are widely recognized and they frequently appear in NFPA 13. Sometimes it leads to confusion. Those are the liter for volume and the bar for pressure.
And this issue of having dual units, customary like gallons and PSI versus metric like liters and bar, It really creates a risk environment, doesn't it? If a U.S. designer works in PSI and maybe a foreign manufacturing team works in BAR, even minor rounding or conversion errors could potentially lead to major design flaws.
Yeah, that's exactly why there's a crucial rule here. A rule designers absolutely need to internalize, maybe even just to avoid litigation down the road.
Yeah.
When a measurement is given with equivalent values in different units, say 100 gallons per minute, GPM, followed by the metric equivalent, the rule is crystal clear.
Yeah.
The first stated value is considered the requirement. That designation just removes any ambiguity about which number the designer has to adhere to. It prevents arguments about, which rounded conversion factor is okay.
Okay, let's transition now to the highlights of the 2019 edition itself. These are the key updates you should probably know about to understand where the industry has moved recently.
Right. The first major change really addressed freeze protection in non-heated environments. Historically, the requirements for protecting piping were, well, highly prescriptive. Do this, use this specific material, apply this exact insulation. But the 2019 edition introduced a new allowance. Engineering analyses are now explicitly permitted to support alternate freeze protection schemes. And that represents a pretty significant shift, moving away from just prescriptive rules towards more performance-based flexibility.
That sounds like a huge win for innovative building designs, really. We also saw updates regarding omission requirements, right? Places where sprinklers can actually safely be excluded.
Yeah, most notably, the standard now allows sprinkler protection to be omitted in elevator machine rooms and also certain associated elevator spaces. This is, I think, a pragmatic change. I mean, fire risk is always present, sure, but the risk of water activation in those specific spaces potentially disabling an elevator bank and trapping occupants, well, that was often considered a worse outcome. Now, the omission is only permitted if specific rigorous criteria are met. It's about balancing that electrical sensitivity against the fire protection needs.
Right, balancing act. And speaking of structural elements, Chapter 9, the one dealing with supports, saw some critical updates too.
Yes. Chapter 9 included new information regarding shared support structures. This clarifies how sprinkler piping can coexist and be safely supported alongside other building services, on the same mounting frameworks. And additionally, they introduced a revised seismic bracing calculation form, which is really invaluable for streamlining the design process, especially in earthquake-prone areas.
The document also made some significant structural improvements to what might be the most complex part of the code, storage.
Oh yeah, Chapters 16 and 17, which cover general storage, were reorganized specifically for better flow and consistency. It makes it much easier to cross-reference between different storage commodity classes now. And crucially, they added a completely new dedicated chapter focused on alternative approaches for storage. This directly addresses the need for guidance on performance-based design, especially when you're dealing with highly specialized or unique storage arrangements that just don't fit neatly into the standard prescriptive tables.
And finally, probably the most interesting update, maybe because it was driven entirely by modern architecture, the rules for cloud ceilings.
Ah, yes. The reality of modern design elements hitting the fire code. Cloud ceilings, those decorative non-continuous ceiling panels, they just don't block heat in the same way continuous ceiling does. So, based on a Fire Protection Research Foundation project, new prescriptive design language was added, allowing sprinklers to actually be omitted above these cloud ceilings.
Okay, so how do you know if you can omit them? What's the trigger?
The key is the gap. The gap between the individual clouds, or maybe between the clouds and the adjacent walls, it has to meet a maximum allowable dimension. And this dimension, it's calculated based on the floor-to-cloud ceiling height. Basically, research figured out that if the gap is small enough, heat and smoke will still vent effectively down into the space below. This ensures the sprinklers mounted below the clouds get the heat they need to operate, and the resulting water pattern isn't compromised by the lack of protection up above those decorative panels.
Okay, let's just focus a bit. Moving from the macro document updates down to the foundational building blocks of system integrity. Before you can install anything, you really have to speak the language of the code, right? And that starts with the jargon decoder.
Yeah, let's start with the absolute cornerstone term, AHJ. The authority having jurisdiction. This is often the local fire marshal, could be the building official, maybe an insurance risk inspector. They are the organization, office, or individual legally responsible for enforcing the requirements of a code or standard, or for approving the equipment or the installation. They truly have the final say. If the AHJ doesn't sign off on some deviation or interpretation you made, well, the project is non-compliant. Doesn't matter what the designer believed.
Okay, next up, we have a more visual structural concept that profoundly impacts sprinkler placement. Obstructed versus unobstructed construction. And this isn't just a general description, right? It's a technical classification.
Oh, absolutely. This distinction is crucial because obstructions, well, they create water-throw shadows, and they can interfere with the upward flow of heat, delaying sprinkler activation. So obstructed construction is defined as structural elements like beams, trusses, or bar joists that materially affect the flow of heat to the sprinkler head or the water distribution from the deflector.
Okay, so what makes it unobstructed then? Where's that dividing line drawn?
Unobstructed construction is when the structural members don't materially affect that flow, and NFPA 13 gives pretty clear dimensional exceptions for this. Construction is typically considered unobstructed if the spacing of structural members, like parallel beams, exceeds 7.5 feet, that's 2.3 meters, on center. So if your beams are spaced, say, 7 feet apart, you're likely in the obstructed category, and that instantly triggers tighter, usually more expensive sprinkler spacing requirements, that 7.5-foot threshold, vital for system designers.
Okay, let's decode a high-hazard concept, one specific to warehouse risk: laced tire storage.
Laced tire storage. It's one of those concepts that perfectly illustrates just how prescriptive NFPA 13 can be. It describes a storage arrangement where tires are stacked so their sides overlap, resulting in this kind of woven or laced appearance. If you can visualize it, it creates these tight, continuous vertical channels.
And why is that specific arrangement considered so dangerous?
Well, those channels, or flues as they're called, they basically act like vertical chimneys. When a fire starts down low, the heat and smoke are just instantly drawn straight up through that lacing. It accelerates the fire's vertical spread dramatically, and often it can outpace the sprinkler system's ability to activate and suppress it effectively. This configuration absolutely demands specialized, high-density suppression techniques outlined in the storage chapters.
Okay, speaking of suppression, let's get to the most fundamental requirement of all: the water supply. Where must the water come from, and what actually constitutes a reliable source?
Yeah, the standard is very specific here. Acceptable sources include, first, a reliable waterworks system, and the volume and pressure there have to be determined by current flow test data or some other approved method. Second, a single automatically controlled fire pump that's installed in compliance with NFPA 20, the pump standard. Or third, a pressure tank installed according to NFPA 22, the TAIN standard. The emphasis is always, always on proven pressure and guaranteed volume for the required duration.
We spend so much time focusing on PSI and flow rates, but what about the silent killer corrosion? Is NFPA 13 finally getting serious about long-term system integrity?
It really is, because corrosion, specifically something called microbiologically influenced corrosion, or MIC, it's a major cause of failure in older systems. And MIC isn't just standard rust, it's actually caused by living bacteria that colonize the pipe walls. They create these concentrated corrosive environments, leading to pinhole leaks or even system blockage over time.
So what does NFPA 13 actually mandate regarding mitigation, especially when you're dealing with potentially high-risk water supplies?
Well, the document defines a raw water source as a supply that hasn't been treated and could contain foreign material, which increases the risk of MIC. And if the water supply or maybe the environmental conditions are known to be corrosive, the owner must notify the installer. And then a formal corrosion mitigation plan has to be developed.
Okay, so what does that plan look like in practice? What are the options?
The options are practical, but they can be costly. You could install pipe that's resistant to MIC, like CPVC, which is mentioned in Annex A, that's a non-metallic option. Or you could treat the water supply with an approved bacterial inhibitor. Or maybe set up a corrosion monitoring station where system components can be physically checked at set intervals. The core idea here is really preventative maintenance against that internal decay that traditional system flushing just won't fix.
Okay, let's move underground now and talk about piping installation, where protection from the cold and the earth itself is key.
Right. Protecting underground piping from freezing is absolutely non-negotiable. The rule is the top of the pipe must be buried not less than 1 foot. That's 300 millimeters below the established frost line for that specific locality. If you bury it above the frost line, you risk the water solidifying, expanding, and rupturing the pipe. Simple physics, big consequences.
And beyond just the depth, the structural relationship between the pipe and the building foundation itself is strictly regulated, isn't it?
That's right. For stability, pipe drains must not be located directly under foundation footings. That's a critical point. Furthermore, the piping has to be installed a minimum of 12 inches, 300 millimeters, below the bottom of building foundations or footers, unless that piping is properly sleeved with an approved material. If you run the pipe too close or directly under a footer, differential settlement of that foundation could actually shear the pipe clean off.
And there's a specific limitation on how far the private fire service mains can run under the actual building structure. Why is there a restriction there?
Yeah, private fire service mains are not permitted to extend more than 10 feet, that's 3 meters, under the building, with only very minor unavoidable exceptions. The restriction exists because penetrating the foundation introduces a significant risk. If settlement or maybe earthquake movement occurs, repair access is nearly impossible without digging up the building. And a break under the structure, that's probably the most dangerous kind of leak you can have. Keeping the majority of the main accessible outside is a critical safety factor.
Okay, so once everything is installed, the proof is in the performance, right? Through acceptance testing. This is the hydrostatic test.
It's the moment of truth, really. All piping that's subjected to system working pressure must be tested at either 200 psi, that's 13.8 bar, or 50 psi, 3.4 bar, in excess of the system working pressure, whichever one is greater. And crucially, that pressure must be maintained for a minimum of 2 hours. That extended hold time is specifically meant to reveal subtle leaks that might not show up instantly under pressure.
But systems aren't perfectly rigid or entirely leak-proof, at least not initially, right? Is there any allowance for leakage during that 2-hour test?
There is, but it's minuscule. The standard does recognize the reality of needing to add slight amounts of water to maintain pressure, maybe due to air entrainment or minor seating issues in joints. There is a, pretty complex formula and a corresponding table, it's 6.30.2.2.6, used to calculate the acceptable allowance of makeup water. It's dependent on the system volume, the pipe length, and the diameter of the system being tested. And I can tell you from experience, that small leakage allowance is exactly why you find every crew chief meticulously checking every single flange gasket.
Yeah.
If you exceed the calculated limit for water addition, the system fails the test, and the cost of remediation just skyrockets.
Okay, beyond just holding pressure, systems need a signal that they are actually operating.
Right. For any system having more than 20 sprinklers, a local water flow alarm is mandatory. The rule states the alarm must activate and be audible on the premises within 5 minutes after water flow begins. This provides immediate notification of a potential fire event and allows the fire department to be called quickly.
Let's briefly touch on piping installed above ground now, particularly systems that might use antifreeze.
Sure. Where temperatures cannot be reliably maintained at or above 40 degrees F, that's 4 degrees C, the system must be protected. Usually this means using a dry pipe or pre-action system, basically. No water sits in the pipe until the system actually activates. Antifreeze is permitted in unheated areas, but it has to be properly mixed and certified.
And there was a critical update regarding testing in a specific type of sprinkler head there, wasn't there?
Yes, very important. If the system is hydrostatically tested with plain water, that water must be completely drained from the entire system afterward, especially if you have pendant sprinklers, to prevent dilution of the antifreeze solution later. But the crucial limitation, and this is a major compliance risk area, is that antifreeze solutions shall not be used in early suppression fast response ESFR systems, unless that specific ESFR sprinkler is explicitly listed for use with that specific solution.
Why are ESFR systems so sensitive to antifreeze? What's the issue there?
Well, ESFR sprinklers are designed for extremely high velocity, high momentum droplet delivery. Their goal is to achieve fire suppression, not just control. Antifreeze actually changes the fluid dynamics, specifically the viscosity and the surface tension of the water. That change can interfere with the ESFR head's ability to generate the required high-momentum spray pattern needed for true suppression. Even a slight change in those fluid characteristics can compromise the entire system's performance, which is exactly why that listing requirement is so strict.
Right. In this section, let's move from the systems infrastructure, the pipes and water, to the nozzles themselves, the business end of fire protection. We really have to start with K factors, which quantify discharge capacity.
Yeah, K factors are fundamental. They define how much water flows out of a sprinkler head at a given pressure. Simply put, the higher the K factor, the greater the flow capacity of that head. Now, for advanced systems like control mode specific application, CMSA, and early suppression fast response, ESFR sprinklers, the standard mandates a significantly higher minimum nominal K factor. We're talking K11.2, which is 160 in metric.
And how does that scaling work when you get into those really massive K factors?
Well, the K factor isn't linear in its impact. Once you move past the standard K5.6, or 80 heads, sprinklers with K factors greater than K28, that's 400 metric, essentially double the flow in 100% increments compared to that standard K5.6. The big benefit of using a higher K factor is that you can achieve the necessary flow density, the amount of water per square foot, at a much lower residual pressure. This really eases the demand on the water supply and the pumping system.
Okay, so beyond flow, we also need to know the temperature rating. This tells us exactly when the sprinkler head is expected to activate, right? And NFPA 13 relies on a pretty vivid color coding scheme for immediate visual
Oh
identification.
yeah, this is where visual literacy out in the field is absolutely key. That temperature classification table, it's table 7.2.4.1, is vital. For example, the ordinary temperature range that's 135 degrees out and 170 degrees out uses either uncolored or maybe black frame arms, and the liquid bulb inside will be orange or red. But when you move up to the high temperature classification, say 250 degrees aft to 300 degrees aft, the frame arms are blue, and the liquid bulb is also blue. So if you walk into a standard office space and you see a blue sprinkler head, well, you know immediately that either that head is significantly oversized for the actual risk, or there's some unusually high heat source nearby that shouldn't be there.
Now, let's talk about what you called the Achilles heel of any sprinkler system, obstructions. A massive part of NFPA 13 is dedicated just to preventing anything from blocking that spray pattern.
Absolutely. The ability of a sprinkler to develop its intended circular spray pattern is vital for control and suppression. And the standard is intensely prescriptive about preventing interference. The relationship between any potential obstruction and the sprinkler head itself is mapped out in really exacting detail.
Can you maybe walk us through a practical example of just how restrictive that table is? Show us the precision needed.
Sure, let's look at table 10.2.7.1.2, which applies to standard spray sprinklers. It directly relates the horizontal distance from the sprinkler to an obstruction. Maybe think of ductwork or a large light fixture. With the maximum allowable distance, the sprinkler deflector could be positioned above the bottom of that obstruction. So for example, if an obstruction is located 4 feet, that's 1.2 meters, horizontally away from the sprinkler deflector can only be a maximum of 12 inches, 300 millimeters, above the bottom edge of that obstruction.
Okay, so if the obstruction is 4 feet away, the water spray needs a full 12 inches of clearance just to successfully pass over it and develop its pattern without creating a shadow underneath.
Exactly. And the closer the obstruction gets, the tighter that rule becomes. If the obstruction is closer than 1 foot, 300 millimeters horizontally, the deflector must actually be positioned at or below the bottom of the obstruction. Literally 0 distance above is allowed. This level of precision, it's all designed to eliminate those water throw shadows. Because during a fire, those shadows become unprotected areas where the fire can just reignite or grow completely unchecked.
Moving to location now. Sprinklers are generally required pretty much everywhere, but there are some critical, recognized exceptions, especially for concealed spaces.
Yes, for certain concealed spaces that are deemed low risk, sprinklers can indeed be omitted. A common example is non-combustible, non-accessible vertical duct shafts. If there's nothing in there to burn and no way to actually access the space easily, the sprinkler is considered unnecessary.
What about small concealed spaces, say, in light hazard areas like offices?
Right. For light or ordinary hazard occupancies, sprinklers can be omitted entirely in small concealed spaces. This applies specifically where you have non-combustible or limited combustible ceilings attached directly to solid wood joists, creating these little enclosed spaces that are 160 cubic feet. That's 4.5 cubic meters or less in volume. The logic here is basically that a fire can't gain enough thermal momentum or have enough fuel load in such a tiny compartmentalized space to pose a real structural threat before the main room system activates.
And just briefly, on electrical rooms, these are often sources of debate because of the potential water damage risk.
Yeah, they are. Sprinkler protection is generally required in electrical equipment rooms. That's the default. However, the rule does allow for omission if specific alternative safety requirements are met. This could mean installing gas-based extinguishing systems, or maybe if the room contains only certain types of fully encapsulated or non-liquid sealed equipment. The absolute key, though, is that the AHJ must approve whatever alternative protection scheme is proposed.
Okay, finally for this section, let's clarify the rules around the fire department connection, or FDC. That absolutely vital link between the municipal water supply and the building's sprinkler system.
Right, the FDC. Every FDC must be equipped with a listed check valve. This prevents the system's pressurized water from flowing back out onto the street. But critically, there shall be no shutoff valve in the piping that connects the FDC to the system. None. This ensures that the fire department always has an open, uninterrupted, and guaranteed route to pump water into and pressurize the system during an emergency. That absence of a shutoff valve is a totally non-negotiable safety measure.
And the physical location of the FDC itself, that often gets compromised by landscaping or maybe building additions over time.
It has to be accessible, period. The FDC must be located at the nearest point of fire department apparatus accessibility. Or, if that's just not possible, at a location specifically approved by the AHJ. The standard is actually explicit here.
Right.
Designers must avoid physical obstacles to access. It even lists things like fences, permanent posts, and even overgrown shrubbery as potential issues. Furthermore, in areas that are subject to freezing temperatures, the piping between that check valve and the outside coupling must be equipped with an approved automatic drain valve. This prevents water from getting trapped, freezing, and damaging the connection when it's not in use.
Okay, this is where NFPA 13 really dives into the deep end of prescriptive engineering, warehouse storage. It's arguably the ultimate fire challenge, requiring engineers to classify the fuel load the commodity with extreme precision.
Yeah, it all begins with commodity classification. This dictates everything: the required water density, the flow rate needed. Commodities are categorized I through 4V, and then you get into Group A, B, or C plastics. Class I is the lowest risk. Think non-combustible products, maybe metal parts, even if they happen to be placed on wood pallets. These require the least amount of water density for control.
Okay, so how do we climb that ladder of risk severity, eventually getting up to Group A plastics?
Right. As the combustibility increases, you move up through Class 2 and 3. That includes things like wood, paper, natural fibers. Then you hit Class 4. Class 4 commodities represent a significantly higher hazard. This category includes products constructed partially or maybe totally of Group B plastics, or products containing free-flowing Group A plastic materials. And Group A plastics, which include really common materials like ABS, acetyl, acrylic, they're generally considered the highest risk because they release just tremendous amounts of heat incredibly rapidly when they burn.
Wait, but Group A plastics classification is subdivided too, isn't it? There's a huge difference between, say, plastic toys in a cardboard box and expanded plastic foam like styrofoam.
Oh, that's a critical nuance. Absolutely.
Yeah.
Expanded Group A plastics like polystyrene foam are arguably the highest hazard classification there is. Why? Because they have both an incredibly high heat release rate and a massive surface area, which leads to extremely fast fire spread. The distinction between free-flowing plastic pellets, cartoned plastic items, and expanded plastic fundamentally alters the protection requirements. It often forces a move from simple control mode density area systems up to early suppression fast response, or ESFR, sprinklers.
What's interesting, though, is that the protection criteria designed for Group A plastics can actually be used as a sort of design default for the lower hazard classes, too.
Yes, that's right. If you design a system that's sufficient to protect the highest hazard commodity you might encounter, say, Group A plastics, then you are automatically meeting or exceeding the criteria for classes 1, 2, 3, and 4, assuming you keep the same storage height and configuration. You see a lot of warehouses opt to protect for the highest possible risk commodity they might ever store, just to maintain flexibility in their operations down the road.
We also need to highlight the impact of the pallet itself. That simple structural foundation of the stored goods can change things drastically.
Oh, this is a detail that trips up compliance constantly. If you take a standard Class 3 commodity, let's say large boxes of paper goods, and you simply place it on a plastic pallet instead of a wood or non-combustible one, the overall commodity classification is automatically raised. It bumps up to Class 4 or maybe cartoned, non-expanded Group A plastic, depending on the specifics. That added fuel load just from the plastic pallet drastically changes the expected fire severity and the heat release rate profile.
Okay, let's move to the advanced protection schemes designed specifically for these high-hazard storage environments. Control mode specific application, CMSA, and ESFR systems. These utilize much higher flows and pressures than standard sprinklers.
Yeah, the design requirements here are highly dependent on numerous variables: the commodity type, the storage height, the sealing height, even whether the system is wet or dry pipe. For high-density rack storage, you often need ESFR CMSA sprinklers with really large K factors, like K25.2, which means massive water delivery is needed.
What is the fundamental difference in mechanism between CMSA and ESFR? How do they work differently?
Good question. CMSA sprinklers are designed primarily for control. They focus on limiting the size of the fire and preventing damage to the sealing structure, basically holding the fire in check until the fire department can arrive for final extinguishment. ESFR sprinklers, on the other hand, are designed for suppression. They create large, high-momentum water droplets specifically designed to penetrate deep into the fire plume and actually impact the burning surface directly, thus achieving true extinguishment, ideally before significant fire growth.
And the height restrictions for these high-flow systems, they're notoriously strict, right?
They are absolutely non-negotiable. Because ESFR, in particular, relies on very specific droplet velocity and momentum to work, Its performance degrades really quickly if the distance from the sprinkler head down to the fire source becomes too great. So depending on the storage height and the specific sprinkler K factor being used, the maximum ceiling or roof height allowed is often capped quite low, maybe 30 feet, 9.1 meters, or sometimes 35 feet, 11 meters. If you go even 1 inch higher than the listed maximum for that sprinkler and storage setup, the design fails compliance because the water velocity reaching the fire is no longer considered sufficient for suppression.
The rack structure itself also has prescriptive spacing rules, specifically designed to help water penetrate down through the stored product, right?
Exactly. This is where the flue spaces come in. We see strict specifications on minimum aisle widths, often 8 feet, 2.4 meters, and also minimum longitudinal flue spaces, usually 6 inches, 150 millimeters, for double row racks. These flue spaces are absolutely vital. If they get blocked by product or if they're designed too narrow, the water from the sprinklers simply cannot penetrate down to the heart of the fire within the rack. And just as importantly, the heat and smoke buildup gets trapped, preventing the upper layers of sprinklers from activating effectively. That 6-inch dimension. It's the consensus-based minimum width required to facilitate both water penetration downwards and heat venting upwards.
Okay, finally for storage, let's examine some unique occupancy hazards that require specialized protection, going beyond the standard storage rules. We can start with commercial cooking equipment.
Right. The standard enforces a crucial safety interlock here. The operation of any sprinkler or automatic spray nozzle designed to protect commercial cooking equipment like deep fat fryers or grills must automatically shut off all sources of fuel and heat to the equipment being protected. That could be shutting a gas valve or tripping an electrical circuit breaker. It stops the fire's fuel source instantly, transforming a potentially fueled fire into a much more manageable, contained fire. And furthermore, all those shutdown devices are required to be the type that needs manual resetting before fuel or power can be restored. This ensures someone has to investigate the cause of activation before restarting the equipment.
Okay, what about water cooling towers? It seems counterintuitive to protect something full of water with more water.
Yeah, it does seem odd at first. For cooling towers, the calculation for the required water supply capacity depends entirely on the separation between the cells. If the individual cells within the tower are separated by approved, fire-resistant partitions, then the required water supply only needs to cover the hydraulically most demanding single cell. Why? Because the fire is assumed to be contained within that cell. However, if those fire-resistant partitions are not provided, the fire could potentially spread across the top deck from cell to cell. In that case, the water supply must be adequate to cover the two most hydraulically demanding adjoining cells. So the integrity of the physical separation directly dictates the required flow.
And maybe the most extreme example, hypobaric facilities, places where atmospheric conditions are manipulated and the fire risk is profoundly amplified.
Ah, yes. These require a completely redundant suppression approach. That's due to the unique dangers of, say, a high-oxygen, low-pressure environment, where fire spread can be almost instantaneous. The standard requires a suppression system consisting of independently supplied and operating systems, both handline hoses and fixed deluge-type water spray systems. And the ultimate test of redundancy is applied here. The failure of any single component in either the handline system or the deluge system must not render the other system inoperative. It's truly life-or-death redundancy for an environment where literally seconds count.
All right, the final sections of the standard deal with motion, how the system needs to handle earth movement, which is seismic protection, and sea movement for marine systems. Let's start with sway bracing, which is all about protecting the pipes from the building during an earthquake.
Right. The primary goal during a seismic event is really minimizing shear strain and differential movement between the piping system and the building structure itself. This is achieved mainly through introducing flexibility, often by using listed flexible couplings at critical points, like where pipes cross building seismic joints, and also by ensuring adequate pipe clearance from walls and floors specifically. The standard calls for a minimum 2-inch clearance for horizontal piping from any structural members that are not directly supporting it.
How do the risers, those main vertical pipes, handle this kind of movement? They seem particularly vulnerable.
They are. Risers that exceed 3 feet, that's 900 millimeters in length, require a 4-way brace right at the top. A 4-way brace is designed to resist differential movement in all 4 horizontal directions, 2 lateral, 2 longitudinal. This is absolutely necessary because risers are the vertical backbone of the system, and they're highly susceptible to shear failure if the building floors move independently during a quake. There is an exception, though, for short risers, up to 7 feet, 2.1 meters, that terminate above the roof assembly or maybe at the top landing.
Okay, what's the difference then between bracing and restraint? especially when we talk about the smaller branch lines.
Good distinction. Bracing is designed to handle the major seismic forces acting on the main pipes, the big stuff, preventing catastrophic failure of the system backbone. Restraint, on the other hand, is a lesser degree of load resistance. It's applied to the smaller branch lines, typically those that are 4 feet, 1.2 meters or longer. Restraint doesn't necessarily need to hold against massive shear forces. Its primary job is to prevent the branch line from swinging wildly during shaking and impacting or snagging on ceilings, light fixtures, or other building surfaces.
So what counts as acceptable restraint for those branch lines then? What methods can be used?
Restraint can be achieved using several methods, things like listed sway braces, which are essentially smaller braces, or maybe wraparound U-hooks that attach to the structure. Or even simpler methods like using heavy-duty materials like number 12-gauge wire, provided it's rated for at least 440 pounds, 200 kilograms. The key installation detail is that the restraint, whatever method is used, must be installed at least 45 degrees from the vertical plane to effectively counteract those lateral swinging forces. The quality of the fasteners holding all this bracing and restraint to the structure seems absolutely paramount, yet maybe frequently overlooked. Well, it's a major area of compliance failure, unfortunately. Crucially, standard powder-driven fasteners, the common Hilti pins used in construction, they're not allowed to attach braces to the building structure, unless they're specifically listed for resisting lateral loads in areas subject to earthquakes. Most are not. Furthermore, any concrete anchors used must conform to ACI 355.2. That's a specific structural anchoring standard, and they have to be installed precisely according to the manufacturer's instructions. Standard anchors just cannot handle the complex lateral and tension loads exerted during a significant seismic event.
Okay, let's pivot now to marine fire protection. Addressing installation on ships and vessels where the motion is constant and cyclical, not sudden like an earthquake.
Right. On a ship, the system has to contend with continuous, often violent motion. Piping bracing must be specifically designed to ensure the pipe will not shift or move the sprinklers relative to ceilings or obstructions due to the vessel slamming, heaving, and rolling. Because of this constant vibration and movement, pipe supports on ships are typically required to be welded directly to the structure, as opposed to using bolted or clamped systems that could potentially loosen gradually over time due to the flexing.
And corrosion is obviously a much greater concern in that marine environment, particularly with constant saltwater exposure.
Absolutely. The standard specifically mandates that sprinklers shall not be rendered ineffective by corrosion related to saltwater entrapment, especially within the return bend or sprig of the pipe connecting to the sprinkler head. This forces really careful design practices to prevent the pocketing of corrosive salt materials that could quickly destroy a vital component like the sprinkler itself.
And what about system control and zoning on a vessel, where containment is arguably even more crucial than in a building?
Yet, alarms must provide a distinct indication for each individual system component that is monitored. This gives the ship's crew precise information instantly about where the problem is. Regarding zoning, sprinkler zones are limited. They shall not encompass more than 2 adjacent decks vertically, nor shall they cover more than 1 main vertical fire zone horizontally. This level of segmentation ensures that if one zone must be shut down for maintenance or damage, it's localized and doesn't compromise fire protection across wide swaths of the vessel. And there are 2 final key requirements for wet pipe systems on ships that emphasize segregation. First, they require relief valves to manage pressure spikes caused by vessel movement or temperature changes. And second, the sprinkler piping shall absolutely not be used to supply any hose connections or fire department or shipboard fire team hose connections. The suppression piping must be dedicated solely to the sprinkler system itself. #down, outro.
It's just astounding when you step back and see how specific the compliance details become. I mean, from the acceptable leakage rate during a hydrostatic test, measured in ounces, to the structural limits that define an obstructed versus unobstructed space, right down to that 7.5-foot mark. We've really seen today that NFPA 13 demands a truly deep dive into prescriptive, often numerical data. It covers everything from complex commodity classification, thinking about Group A expanded plastics or those lace tires, all the way to critical structural geometry, like needing 4-way seismic bracing on risers.
Yeah, the takeaway here, I think, is that precision is absolutely paramount. And the highly prescriptive nature of NFPA 13 is really born from decades of fire testing, loss experience, and detailed risk analysis. The difference between an effective code compliance system and one that might fail under fire conditions, well, it can genuinely rest on whether that underground pipe is buried 11 inches or the required 12 inches below the bottom of a foundation footing, or whether that flue space in the rack storage is 5 inches wide instead of the required 6 inches. These detailed rules exist because those seemingly small variances can absolutely dictate whether a fire is controlled early or whether the entire system is ultimately overwhelmed.
It truly is a masterwork of engineering codification that defines the rules of safety for so many buildings. And that brings us perfectly to our final provocative thought for you, the listener, to consider. It involves a key and sometimes confusing interaction between fire codes and electrical codes. NFPA 13 explicitly prohibits using the sprinkler system piping as a primary grounding electrode for the building's electrical system. However, NFPA 70, which is the National Electrical Code, requires that all metallic piping systems, including sprinkler pipes, be bonded to the electrical grounding system. This is done to disperse stray electrical currents and equalize electrical potential.
Right. And that difference between grounding and bonding is subtle, but absolutely crucial. You cannot use the piping as the main path to ground the building's electrical service that could introduce massive, dangerous electrical surges onto the pipe during a fault. But you must bond the piping to the electrical grid. This prevents damage from smaller stray currents, maybe from equipment faults, or even lightning nearby that could cause corrosion or degrade the pipe integrity over time. So understanding that distinction between prohibited use as a grounding electrode and mandated bonding for electrical safety, well, that's essential for maintaining both fire safety integrity and the long-term lifespan of your fire suppression system. Something to definitely think about the next time you inspect a project site.